Welcome back. I hope chapter 1, which are purely depending on depending on only fundamentals, and those things will help you to understand the remaining topics what we are going to see from now onwards in a better way. Okay. Okay. Chapter 2. BJT amplifiers. Again, there are many subtopics and concepts to be covered under BJT amplifiers, but whatever it may be, it will come under category BJT amplifiers only. Okay. I think as I discussed in the introduction class about BJT amplifiers, we are going to deal two types of analysis, AC analysis or DC analysis, right? When I say AC analysis, we are going to speak about only AC signals. When I speak about DC analysis, I am going to speak only DC signals or biasing and Q point stability. But after covering both DC analysis and AC analysis, I am going to combine DC plus AC, then that is what is your final circuit, and that is what I can say the final BJT amplifier, right? But from the starting point, we are not studying the final BJT amplifier. From starting point, we are going to study only AC circuits and only DC circuits, but after combining, because we need to get what is the best configuration from AC analysis, what is the best configuration from DC analysis, then we need to take best from AC configuration, best from DC configuration, combine both of them, then it will give you the best or the final. It's not best, you will get the final amplifier, then that is what is your BJT amplifier. Okay. Now, maybe now the subtopic, right? You can say AC analysis. Therefore, the subtopic name, instead of saying simply AC analysis, I am just saying that this is BJT small signal AC analysis. Why it is called small signal? This is not the time to explain what is small signal. Give me some time. Therefore, you will understand the meaning of small signal. BJT small signal AC analysis. Instead of simply AC analysis, I am saying BJT small signal AC analysis. This is what people call. This is what is subtopic. Okay. That's fine. Now, when I say BJT small signal AC analysis, right? And I want to give you before starting the BJT small signal AC analysis, I want to give you a small comparison. Therefore, it is easy to understand with respect to other devices. Okay. Don't write, just listen here. Now, in the last session, I told that when you take switch action or amplifier action, I told it is only steady state equation or DC equation where timing information is not there. But if I incorporate timing information, that is nothing but AC analysis, right? Therefore, and let's see at a given frequency, which is not zero frequency and not infinity frequency, how that equivalent circuit will change, which is basically dynamic circuit or dynamic resistance if it is two-terminal device. Okay. Maybe before going there, just you can take a table to compare. Okay. Now let us say this is what is DC analysis or DC circuit, I can say, and this is what is AC circuit or AC equivalent. DC equivalent and then AC equivalent. Okay. Now let me start with resistor. Okay. Let me start with resistor. Now when I say this is what is the resistor, now tell me the resistor, right, under DC, what is this represented? Resistor only. It won't change. This is resistor only, because the resistance value, when I say resistor, obviously resistance value, the resistance value won't change with respect to what? Frequency. But I told you at very high frequency, like hundreds of megahertz, like 800 to 900 megahertz or in the order of gigahertz, because of skin effect, the resistance changes, but I'm not going to that much frequency. When I say AC frequency or AC analysis, less than 100 kilohertz or less than 1 megahertz. That is what I can say. Okay. Therefore, I can say less than 1 megahertz. Now, if I say that, now if you take resistor, now what is this? This is resistor only. Okay. Now, number 2, inductor. Okay. Now, what is that in DC? For DC, inductor acts as a short circuit. Therefore, this is what is acting as a short circuit. Your inductor will be acting as a short circuit. Now, this is what is ideal model. But if you take practical model, because the inductor is also a wire, that wire will have some resistance. Therefore, you can say that is nothing but your wire. Okay, that you can take it. That is fine. Now, for AC, that is what people say, it will have some impedance, right? It will have some impedance or reactance. Therefore, what is that? X is equal to 1 by, if I take only magnitude, right? What will be? That is nothing but J into omega L. This is what is your reactance. Okay, or you can say that is nothing but your Z instead of reactance. I can say this is what is your impedance, Z. Now this is what is here. I'm giving only ideal model. I'm not giving practical model, because you know the difference between ideal model and the practical model. I'm just giving level 1 or first approximation. Third one, the capacitor. Now if you take capacitors, for a DC, capacitor acts as a open circuit, and for AC, capacitor acts as a, it is not short circuit, but it will have connectivity between two terminals. Okay, then if you take Z value, that Z is equal to 1 by J omega C. You can take manual and all later, but that is what is the Z, which is what is offered, right, with respect to the frequency. Now, actually, using these things, I am going to exploit to next. Let us say the PN junction diode. If you take PN junction diode, right? Let me take third approximation, because we have 3 approximations, right? But whatever approximations I gave, remember, that is under DC analysis. Whatever approximations I gave, that is under DC analysis. Therefore, if you take, let us say, third level is nothing but what? Level 3 or practical model. Then this is nothing but a resistor and a battery. That is what I gave. And this is what I told, the forward resistance RF, and this is what is our V gamma. This is what I told, right? Therefore, I am using third approximation. Therefore, third approximation, because if I use first approximation, there is no difference between DC and then AC. Just to show some difference between DC and then AC, I am just taking third approximation, right? But I don't have space, or otherwise I can say under DC, first approximation, second approximation, third approximation. What is that exactly under AC? First approximation, second approximation, third approximation. If you want, I can give you like that also. Okay, maybe that will be so clear for you. Let me give you. Anyway, I need more space. This is not enough. Therefore, the same PN junction diode under DC, right? This is what is under DC, and this is under AC, right? Now, if you ask me the PN junction diode, right? This is what your PN junction diode. Now, if you ask me, because our equivalent circuit is different, this is what your PN junction diode, right? Now, first approximation, that is nothing but what? Short circuit. And the second approximation, that is nothing but battery, which is V gamma, and third approximation, that is nothing but resistor and V gamma. This is your RF, and this is what is your V gamma, right? And if you take exact model is nothing but, therefore this is what is first approximation or ideal model, first approximation, and this is second approximation, and this is third approximation. Maybe if you continue, you'll get exact model. What is exact model? Therefore exact model equation is nothing but, this is what is supported by I is equal to I naught into e to the power of V by eta Vt minus 1. This is what is, this is what is your PN junction diode. Okay, this is supported by I is equal to I naught into e to the power of V by eta Vt minus 1. Okay, this is what is the exact equation. Now coming to, just wait, I'll tell you. I think we had seen this, right? This is what I gave. Therefore that time only I told there is no time information. These are all under steady state. Okay, therefore if you take first approximation, which is nothing but your ideal model, this is nothing but your ideal model or level 1, and you can say practical model. These two are practical models. Therefore these two are practical model, and you can say, you can take, this is what is exact model. This is what is your exact model, practically exact model. Okay, now fine. Now if you take the AC part, right, then what do you mean by AC? Same thing with respect to frequency, the resistance, or with respect to frequency, how is it changing? See, because if you take in the case of 1 and then 2 and 3, there is no voltage and there is no current, simply resistor or impedance, right? That is fine. But coming back to your PN junction diode, equivalent we are represented with some voltage and then resistor. Maybe if you take third approximation, that's why earlier I was trying to take this, because I have resistor as well as voltage source, right? Therefore now if you say here, right, this is already dynamic resistance which you already calculated from exact equation. Then, right, how will you calculate this V gamma? Sometimes people will ask you to use exact model only, even though this is DC analysis, because this is what is capital I and this is what is capital I naught. Capital I naught, I is equal to capital V and then capital I. Therefore this is what is the relation between I to V. Therefore DC voltage to DC current. Therefore if you use exact model, you will get it. Okay, maybe if you don't want to have any confusion, this is what your exact model. Now if you ask me in the case of AC analysis, actually I don't have space here, let me expand here, you try to manage. Okay, this is what your PN junction diode. Okay, now coming to your first approximation, there is nothing, whether it is DC or AC, it is short only. Okay, under AC analysis. Then what about this? We have to replace with its AC resistance or dynamic resistance. That is what we need to have. Therefore now tell me, right, what is this V gamma? V gamma will not change with respect to frequency of the signal what you are going to excite across your PN junction diode, right? Therefore the V gamma will not change with respect to frequency. Then what does it mean? With respect to frequency is nothing but what? The change in the voltage, the change in the current with respect to time. Very simple. But what is the time? That is what is very important. Within small time, if it is changing very quickly, high frequency. Within the same time, if it is changing very slowly, low frequency. Very simple. The signal which is changing with respect to time is AC signal or non-zero frequency signal. But if the signal is changing very quickly with respect to time, then that is what is high frequency, else low frequency, etc. Now we know that this V gamma is not changing at all with respect to time, right? Therefore if V gamma is not changing with respect to time, during AC analysis we will not take the account of V gamma, because the change in V gamma is equal to 0. Therefore because the change in V gamma, delta V gamma, the change in V gamma due to frequency is equal to 0, then that is also represented like short only. That is also represented like short only. Then coming to third approximation, right? Here, yes, your V gamma is not changing with respect to frequency, right? because there is a DC voltage. If there is a DC voltage, we need to take V1 minus V2 with respect to time, right? V1 at a given time, V2 at a given time. V1 minus V2 divided by, means delta V by delta T. T is changing, time is changing, but V1 minus V2, that is not changing because this is constant. Therefore, we have V gamma, the change in V gamma is equal to 0. Because during AC analysis, we speak about only change in quantities, how the circuit is responding or circuit is behaving for change in voltage, change in current with respect to time. Therefore, what is this V gamma change with respect to time? That is what is not there, but this RF is the one which is what is described already. The change in voltage across PN junction node, the change in the current is described by your small RF, which is already represented in third approximation. That will be there as it is. Therefore, it is simply small RF. What is the small RF? Eta Vt divided by I, which you already derived. Let me tell you a point, very important note, right? During AC analysis, if you take your PN junction diode as some forward resistance and shorting the V gamma means your V gamma 0. No, remember that is for our understanding purpose. That is for our analysis purpose. While doing AC analysis, we are analyzing the circuit for AC signals. Well, we are analyzing for the AC signals, right? We don't need to bother about the V gamma because that is not going to change or that is not going to disturb our AC functionality. Means we are trying to observe what is change in voltage, what is change in current with respect to time. Then that V gamma will not impact those things. Reason, the V gamma is not changing with respect to time. Therefore, the DC quantities will be cancelled. The DC quantities will be cancelled. Then you can say simply delta V by delta I, right? That part I will explain with respect to one example. Therefore, you will understand very clearly. Not only for PN junction diode, I will explain for PN junction diode, for BJT, for MOSFET. But give me some time. Therefore, you will understand. Maybe after explaining that, if you come back to this analysis, you will understand 100%. Okay. Now, this is what your RF. Now, if I say the DC current equation, now we should not say I is equal I naught into e to the power V by eta Vt minus 1. Now, we need to take the relationship. Therefore, di by dV. Therefore, always represent di by dV. Therefore, di by dV is equal to, we already derived, which is nothing but I by eta Vt. This is what is the relation. di is equal to dV into I into eta Vt. That is what is your forward resistance into delta V. Therefore, what is the meaning of it? I can say this is nothing but, therefore, di is nothing but dV into forward resistance RF, which is nothing but your I by eta. Sorry, this is fine. Di is equal to dV into I by eta Vt, where I by eta Vt is nothing but 1 by RF. Okay, that is fine. Therefore, this is nothing but which is nothing but dV divided by RF. That is what is your RF. Okay. Now take it. Similarly, I will give it to you. I will try to give you for BJT as well as MOSFET. That is what we are going to see. See, this is what is kind of another summary with respect to DC and then AC, because as I told you before, BJT amplifiers we are going to analyze with respect to DC signals and for DC signals and for AC signals. For DC how it is acting, for AC how it is acting, that is what we are trying to see. Because in the case of passive elements, we don't have any voltage and current internally. Therefore, either it is short circuit or open circuit, that is straightforward with respect to frequency. But if you come to PN junction diode, right, because we have some DC voltage, that is what is equivalently represented. That is nothing but the V gamma, the drop, which is what is there inside the PN junction diode. Therefore, now it is acting as a battery, or it is opposition by the depletion region. What you have, that is not required in the AC analysis. That doesn't mean that we are shorting it. It is not shorting. We are not taking that into account while doing AC analysis. That is the meaning of it. Okay. Inherently that is present, but not required to show in AC analysis. Even though you show, doesn't matter, but that is not having any significance for AC analysis. You will understand. Give me some time, you will understand. Therefore, what is the observation? During DC analysis, if there is an inductor in the circuit, short it. If there is a capacitor, open it. For AC signals, if there is an inductor, replace with it at very high frequency, you can say open circuit, and For AC analysis, you can say this is what is having some impedance at very low frequency, very high frequency, you can short it. That is what people say equivalent to short circuit, and inductor equivalent to open circuit, but it is at a very high frequency, not for every frequency. This part we already derived in the starting of the sessions. Therefore, di by dV is already derived from this equation. Therefore, during DC analysis, see, this is what your exact model. Remember, this is what is our ideal model, then second approximation, third approximation. Therefore, third approximation is almost close to your exact model because we are accounting this RF with respect to this. Else, if this RF is given as a constant and it is independent of the bias current, then you can say there will be some error, but strictly speaking, if you account that RF also with respect to the DC current equation, then both are same indirectly. Therefore, here also the delta V gamma is equal to 0. This is exact model. And this is what is this is first approximation, second approximation, and third approximation. Similarly, I will give you for BJT and MOSFET, then we can start the equivalent circuit of BJT from mathematical analysis. Okay. Over. Now write down fifth one. right? Now fifth one, BJT. Okay, let us take only ideal model, that is enough because this is bigger. Now if you take BJT is nothing but, instead of writing, it is nothing but the symbol, right? This is collector, emitter, base. Okay. Now what is this? This is what we are representing with a current source, right? Therefore what is that current source? If you take ideal model, the current source whatever you have, right, that is nothing but, here this is what is represented with between collector and emitter. This is already, I already told you. Therefore what is this IC? IC is equal to beta into IB, because it is not simply a current source, it is current control current source, right? IC is equal to beta into IB plus 1 plus beta into ICBO or IC0, right? Done. I am taking only active region, okay? I am not taking saturation and the cutoff, or I am taking only amplified portion. And this is what is ideal model. Now coming to the AC analysis part, therefore now tell me what is this? This is represented, let us say this is C and then E, it is also a current source, right? During AC, then whatever current you have, this is nothing but your, remember this is capital IC, because I am representing capital IC, capital IB. Now I am going to represent small IC, therefore this is now small IC. What do you mean by small IC? I will explain. Maybe here I can correlate a little bit, but in the case of PN junction I did not give you because I derived something and then we have given. Further we need to solve a problem, then you will understand. But here I can explain a little bit between DC and then AC. Okay. Now what is AC analysis? Let us take at a time t is equal to t1. At a time t is equal to t1, or I can say all the timing is there. Let us say we have current IC1 is equal to beta due to IB1, right? IB1 into plus 1 plus beta into IC0. Okay. Now this is what is DC equation. Point to point, static to static, static current to static current, DC current to DC current. But we know that this IB1 is becoming IB2 with some time, right? With some time. But it is a change. Okay. Then your IC1 will become IC2. Then IC2 is equal to beta into IB2 plus 1 plus beta into IC0, right? But I am looking for the change in the current. I am looking for only the change in the collector current. Therefore, because that is nothing but AC signal. What is AC signal? The signal which is changing with respect to time. That is what is called AC signal. Therefore, I am looking for change in the current. If you come to DC analysis, I am looking for DC current. What is the current? Because of the base current. If IB, then IC. It is like point to point. If IB, IC. That's it. But here I am not looking for IB to IC. I am looking for what is change in IC because of change in IB. If I want to know change in IC because of change in IB, we need to take IC1 because of IB1, IC2 because of IB2. There is a change in IB, IB2 minus IB1. Then what is the change in IC? IC2 minus IC1, which is nothing but change in IC. Therefore, tell me what is IC2 minus IC1. Therefore, if you take with respect to time, right, that the time is not shown, but there is a time, that is nothing but frequency content. Therefore, now what is that? Then if you take this minus this, whatever DC quantity, whatever constant quantity between IC1 to IC2 are with respect to time, if there is nothing which is not changing, that will be cancelled. That is what I told. During AC analysis, if there is anything which is not changing, that will be cancelled when you take delta, because while doing that delta, when you take this minus this with respect to time, the constant factor whatever you have in the equation, that will be cancelled out. Okay. Therefore, this 1 plus beta into IC0, 1 plus beta into IC0 is constant at constant temperature. Here temperature is not changing. If you put all variables at the same time, it is too confusing. Therefore, when I do AC analysis, only time is changing, then remaining like temperature is constant. Then this is what is constant. Then if you do, you will get beta into IB2, right? And this will be cancelled. Therefore, minus beta into IB1. This is what you get. If I take beta common, IB2 minus IB1, this will be cancelled. Then tell me, this is what people call it as, delta IC. I am giving you the terminology, right? Then what is this? This is nothing but beta into delta IB. right? Therefore, this is what is beta AC. For AC signals, what is your beta? Therefore, that is what your beta AC, or you can call it as beta. Anything is fine. Okay. Then the delta IC is nothing but the change in current. That is what people represent it as small IC. Small letter is nothing but the change in quantity with respect to time. Instead of representing with delta IC, it is what is represented with simply small IC. Therefore, what is small IC? Small IC is equal to beta AC into small IB. Therefore, this is what is your DC equation for DC analysis, and this is what is your AC equation for AC analysis. Means in AC analysis we are looking for what is change in IC because of change in IB. Okay. Therefore, for AC analysis we should not use this equation. We should use this equation. Okay. For DC analysis we should use this equation. We should not use this equation. Therefore, there is a difference between DC to AC. That is what is very important. Okay. Therefore, that is the reason why I have represented the small IC, but this is what is controlled by small IB. But what is that relation? Small IC is equal to beta into small IB. I hope everybody understood. Okay. What I want to say or what I want to highlight is in a given DC equation, if there is anything, not only equation, any circuit in a given DC equivalent circuit, if there is any DC source or voltage source or current source or anything which is constant, right? Then you can take change in that constant, you can take it as 0. Okay. That's why the change in the quantity which is common for both the equations with respect to time, that is cancelled, and then you got it. Okay. Write this equation. Similarly, I will explain for MOSFET. Let me have some water. Again, I am stressing the point. These equations are valid only when the transistor is in active region, only when the transistor is represented with a current source, right? Therefore, we can use it for amplifiers. That's why for your amplifiers, I always say your IC. When I say IC in the case of amplifiers, right, that is nothing but small signal, which is changing with respect to time. Small IC is equal to, need not say every time small IC, small IB. IC is equal to beta into IB. For AC analysis, by default, that is small IC. If this is over, okay, then I'll explain for MOSFET. Okay, now let's write sixth one, MOSFET, and with that, that is over. If you take MOSFET, right? Now, see, I am giving only for level 1 or first approximation or ideal model. Okay. For the level 2, that is what we are going to see, equivalent circuits of your MOSFET for AC circuits and all. Those are all level 2 equation, level 2 equivalent circuits. But just to differentiate between DC and AC, I am taking only level 1 or ideal model. Now, what is this? This is nothing but a current source between drain and source, but this current is controlled by gate to source voltage, capital VGS. Therefore, now what is this current? This is capital ID. Therefore, capital ID, capital VGS. What does it mean? DC voltage to DC current. That is what your DC analysis. Therefore, now tell me what is the relation? We know that ID is equal to mu n Cox. I am taking only saturation or current source, right? Therefore, W by 2L into VGS minus VT whole square. Level 1. I am not taking 1 plus lambda into VDS. You can take it, but just to compare between DC and AC, this equation is enough. Okay. Therefore, this is what it is. Because normally people call it as mu n Cox W by L is process dependent parameter, because mu Cox W by L people call it as device transconductance, which is Kn by 2, where mu n Cox W by L, this can be treated, and which is nothing but VGS minus VT whole square. This is what it is. This is what your ID. Anything is fine. Okay. Now coming to AC analysis. Right. Now how will you represent? Remember, here also it is a current source. Here also it is current source. This is drain. This is source. But now this is what is controlled by whom? Now here I am looking for change in ID. I am looking for change in ID. Here capital ID with respect to capital VGS. Now I want to know what is change in ID because of change in VGS. That is what I want to know. Therefore, I want to know this is due to small VGS, not capital VGS. Okay, let's see. How will you get it? Don't say small ID is equal to mu n Cox W into small VGS minus VT whole square. Can you write like that? No, we cannot write like that. Okay. For that we need to do the analysis. What is that analysis? I think the same thing we did in the case of PN junction diode, right? The same way we can do it, right? What is that? Maybe you can do ID1 is equal to, because this is constant, let me take it as Kn by 2 into VGS1 minus VT whole square. Your VT will not change with respect to time, right, or with respect to the signal excitation. The VT is function of temperature, function of doping concentration, function of thickness of oxide. Once device is fabricated, temperature is constant, your VT is constant and Kn is constant. Okay, only the variables are input voltage and then output current. That is what you are looking for. Input voltage to input current or output voltage to output current. Only signal variations, not other parameter variations. Okay. Now, but during DC analysis, we will not bother about signal variations. We will bother about all these things. The VT variation, Kn variation, right? In the case of BJT, IC0 variation, beta variation, because those are also important. Those are also changing something. There we will speak about DC analysis. There we will speak like Q point stability and all, right? But whatever may be it for DC analysis, these are all important. These are all important. But how are they controlling your Q point and all? That is what we need to see. That is from DC analysis. But during AC analysis, we will not bother about those DC quantities, right? Only we bother about only signals variations, right? Now let's see what is ID2. Therefore, this is what is ID2. ID2 is equal to Kn by 2 into, right, VGS2 minus VT whole square. Like your BJT, this is not straightforward because we have square term, right? Because we have square term, right? Then we need to subtract. Therefore, what is this? This is nothing but ID2 minus ID1. Therefore, what is ID2 minus ID1? Maybe when you subtract, your Kn by 2 is constant, right? Therefore, if you take Kn by 2, that is what is constant, right? Into, what is this? This is nothing but your VGS2 minus VT whole square minus VGS1 minus VT whole square. Okay, when you subtract you will get something, right? I am not deriving that part for the time being, right? You can take it when you solve, you will be getting it, right, approximately after some assumptions, because I want to explain something later. If I derive, I need to explain that part, therefore it is difficult to understand for you, but I think it is easy for you mathematically. What to do? A minus B whole square, A square plus B square plus 2AB. Similarly, A plus B whole square, A square plus B square minus 2AB. Then VT square will be cancelled. You will get VGS2 whole square, VGS2 whole square is 2 something. If you do, you will be getting, after neglecting few things, what you get? You will get something like this. Maybe if you do this, this is nothing but Kn by 2. Then you will get approximately, then you will get 2 into whatever you have, like this is what you will get, or I can say this part I will derive, but I can say directly with something, some constant into you will get small VGS, or I can say VGS2 minus VGS1. But remember, I will come back to this point because I need to explain something, then only you will understand when I do, because I will do some approximation. But if I don't explain qualitative part of that approximation, it is difficult to understand. To explain that qualitative understanding, for that I need a few amplifier configurations, then only I will explain that approximation which is valid, then we can derive it. But what it may be, I want to say something. Therefore, this is what it is. Therefore, what is ID2 minus ID1? This is nothing but ID2 minus ID1. Okay. Therefore, what is ID2 minus ID1? That is nothing but delta ID is equal to some constant into, right? That constant is nothing but Gm. Why it is Gm? I will explain later. Therefore, this is nothing but delta Vg. Yes, delta VGS. Therefore, small ID is represented as small ID is equal to Gm into small VGS. But what is that Gm and all? I will explain later on. But for the time being, you can take it. Therefore, this is some constant. Therefore, this is what it is. Now, if you see here, this is what is your ID. That is what is DC equation. But what is the change in ID because of change in VGS? Is small ID is equal to Gm into small VGS. Okay. Therefore, remember, this is nonlinear equation. This is nonlinear equation. This is nonlinear equation because it is having square term. It became linear. Why it became linear? That is what I will explain further. We need some approximation. For the time being, you may say that you have some doubt. You can keep something doubt, bigger DOU, BT, and then you can keep it. But after explaining the MOSFET, BJT amplifiers and the MOSFET amplifiers, and then come back, then you see whether it is doubt or not. It won't be doubt, it will be clarified because I will be clarifying it. Okay, that's fine. And now, this is what your ID is equal to Gm into VGS. Therefore, now what I want to say, capital ID to capital VGS, that is for DC, but small ID to small VGS, that is what is AC. Therefore, the small ID, change in current to change in VGS is this. Therefore, this is what we are going to use. Remember, this is what is level 1. Okay, this is what we are going to use in the AC analysis. But anyway, I'll complete completely, including channel length modulation, etc. between input to output. That is what we are going to get from MOSFET equivalent circuit. That part we will see when I start MOSFET amplifier. But this is what is the summary part. Okay, take it. If there is any DC quantity, that will be cancelled during AC analysis. That is what is very important point. And if there is any frequency dependent parameter like inductor and capacitor, those also will be acting accordingly with respect to frequency. Maybe just to correct, you can say this is what is AC, right? Therefore, I'm just correcting something. Maybe you can write in the previous also 1, 2, 3, 4, 5 and all. Small signal, low frequency. Instead of that, small signal and a low frequency. You will understand why it is small signal and why it is for low frequency. Okay, but you need to give me some time until we complete BJT amplifier and MOSFET amplifiers. Then you will understand why it is small signal and why it is only for low frequency. Okay, low frequency means the signal should change, the signal amplitude should change, should not change very quickly with respect to time. If it is changing means that is what is called high frequency. For high frequency, again we need to incorporate something, that's what, on top of this. Therefore that part I will explain later on. If I explain everything, that's what I told, we need to go by step. If I explain everything, we will not understand. AC. Okay, now let me say something, you may laugh, but let us assume that we didn't study anything till now, we didn't look into all fundamentals till now. Assume that we don't know. Just assume that we don't know. Because normally we will try to keep referring the fundamentals to understand, I agree. But even though we don't know what is there inside the BJT and then what is cross-sectional view and how it is doing the amplification, even though you don't know all those things, but we can get it, right? The equivalent circuit of BJT using two-port network analysis. Therefore, this is another way. There are two ways, but giving you the same solution, but different ways will have their own advantages, their own disadvantages, right? Therefore, the mathematical analysis will give you the destination or the source or the solution, but we don't know how we arrived. But qualitative part, based on device operation, understanding what is phase width modulation and getting the equivalent circuit, right? Then it will give you the solution, but it will take time, but you know what are you doing and then why are you doing and then why that is what is changed, all those things. But quantitative analysis, you'll get the answer while doing some mathematical analysis, you'll get the answer, but you may not know why it is not doing like that. Qualitative analysis will be missed in the case of mathematical analysis. Okay, let's keep the qualitative part, whatever we had seen till now, aside, and then let's go ahead with the BJT small signal AC analysis. I'm speaking about only AC analysis. Therefore, I'm going to speak about only change in IC, change in IB, change in VBE, change in VCE, right? Only change in quantities with respect to time. Therefore, I'm going to speak about only AC signals. If I speak about only AC signals, right, then let us say this is what is, before going to the BJT, let us say this is what is black box. The black box can be like, remember BJT, can be UJT, can be JFET, can be MOSFET, can be something, you may get some other device in future, right? Whatever maybe it should be a current source to get amplification, current control current source or voltage control current source to get amplification, whatever it may be, let us take it as a black box. Let us take it as a black box and let's try to analyze using two-port network analysis for small signals, not for DC signals, but two-port network analysis is valid for DC signals also. But here I'm saying because BJT small signal AC analysis, therefore it is only for AC signals, then let's see, okay. Now, when you take two-port network, when you consider two-port network, right, it is defined with two ports, right? What is a port? Pair of signals. Therefore, this is what is your input port, right? And this is what is output port, right? Therefore, this is what is your two-port network. The two-port network can be modeled or characterized with respect to electrical signals, which are nothing but V1 and then I1, V1 and I1. If you observe clearly, I am representing with what? Small letters, means only AC signals, the signals which are changing with respect to time, right? Similarly, small V2 and then I2. But remember, the network, from network analysis, whatever two-port network analysis we are doing, that is valid for any signal, whether it is DC signal or AC signal. But here I am saying that I am applying only for small signals. Okay, you will understand later on, and it is true, the equivalent circuit what you get for BJT or MOSFET, whatever it may be, using two-port network analysis, that is true only for small signal inputs or AC signal inputs, small signal AC inputs. Okay, now if I say that, right, but if you consider BJT, how many terminals do we have? We have 3 terminals, right? But if you take two-port network, we have 4 terminals, right? If you have 4 terminals, I want to make 3 terminals and 1 terminal common for both the input and output. Therefore, I can use the two-port network analysis for the BJT also, where BJT is having only 3 terminals, right? Therefore, if I do that, therefore, can I write into 3-terminal device where 1 terminal is common for both input and output? Therefore, now 1 terminal is common for both input and output. Now this is what your input port. Let me define with input voltage V1 and input current I1. Therefore, this is the current which is entering into your black box. That is the two-port network notation. Similarly, your output voltage V2 and output current which is entering into your output port. That is nothing but your two-port network notation. If this is what is the case, I want to characterize the black box with respect to V1 I1, V2 I2, I1 I2, I1 V2, V1 I2, I2 I1, so many combinations we have, right? Therefore, let us have the combinations and let's see how many models we can get. Therefore, let's pick up one of the models which are derived, then let's use for BJT. The same thing you can do for MOSFET, right? Then you can do the same thing. For any system, but it should be defined externally with input voltage, input current, output voltage, output current. Then you can model any circuit or system or anything with respect to two-port network analysis. Okay, but remember here I am saying V1 I1 because electrical domain we have input voltage, input current, right? Maybe in mechanical domain you can have like that also. It's not input voltage x1 y1, x2 y2. It could be anything, right? But I am applying for V1 I1, V2 I2. Okay, take it. Let me stop the session now. Let me continue from the next session onwards, and then let's see how to define the variables or how to define the model. Then let's pick up one of the models. Okay, thank you. Maybe 2 minutes the video will be there. Now you can continue to draw. Then next session onwards I'll be doing the continuation part. Okay, thank you.